In, in this session, we consider a few more examples of how to calculate the derivatives of real-valued functions from the limit definition of the derivative. And we give some examples of where the derivatives of a function do not exist. Let me remind you of a few things. The derivative is found by taking the limit of this difference quotient. That's what the derivative is, if it exists. If you want to consider the derivative of a function as another function derived from the first function, then you take this difference quotient, limit as h goes to 0 of f of x plus h minus f of x over h. You take the limit of that difference quotient, and you'll get that derivative. You'll get that derivative of f at x, provided that the derivative exists. And we have already found the derivatives of 1x, x squared, x to the n for n an integer. And if we know the derivatives of f and g, then we know how to find the derivatives of f plus g, f minus g, 1 over f, when f doesn't take the value 0, and c times f. And we also said that if you had a function f and you wanted to take its derivative, if you could find its derivative at x naught and its value at x naught, then you could get the linearization of f as L of x is equal to f of x naught plus f prime at x naught times x minus x naught. This is a monomial function such that the linearization agrees with f at x naught, and the derivative at x naught of the monomial function agrees with the derivative of f at x naught. And the graph of the linearization of f at x naught is called the tangent line to the graph of f at x naught. Okay. Now we take a few more examples of calculating derivatives. So the derivative of the Heaviside function at 3 different points. So we've got this function, h tends r to r. It takes the value 1 for non-negative input, and it takes the value 0 for negative input. Let's find the derivative of this Heaviside function at 1, minus 1, and at 0. Okay, so if we had a rule for this function, then we just apply the rule. We don't have the rule, so we use the limit definition to find the derivative. Okay, note that for x close to minus 1, remember we're taking the limit as x goes to minus 1. So we're letting x get arbitrarily close to minus 1. So if x is very close to minus 1, which is negative, then x must be negative. And when x is negative, then the Heaviside function returns 0 for h of x. So then h of x is equal to 0. H of minus 1 is equal to 0. The difference between h of x and h of minus 1 is 0 minus 0 equals 0. Then the difference quotient is h of x minus h of minus 1 over x minus minus 1. We've already found that the numerator is 0 divided by x plus 1, which is 0. So then the derivative is the limit as x goes to minus 1 of the difference quotient. And so that's the limit as x goes to minus 1 of 0, which is 0. Okay, so the derivative of the Heaviside function at minus 1 is 0. Okay, now we want the derivative at 1. So for x close to 1, which is positive, we must have that x is also positive. And so h of x is equal to 1. Okay, so then h of x is equal to 1. H of 1 is equal to 1. H of x minus h of 1 is 1 minus 1, which is equal to 0. So then the difference quotient is h of x minus h of 1 over x minus 1. That's equal to 0 over x minus 1, which is 0. Then the derivative at 1 is the limit of the difference quotient, which is the limit as x goes to 1 of 0, which is 0. Okay, now we consider the derivative at 0. So to get the derivative, if it exists at 0, we have to take the limit as x goes to 0 of h of x minus h of 0 over x minus 0. Well, if you have h of x with x being very close to 0 but positive, then h of x is 1. And if you have x less than 0, very close to 0 but less than 0, x is negative, then h of x is 0. So calculating this limit would be awkward directly. So what we do is we say, well, the behavior of the function, the form of h of x changes at x is equal to 0, exactly at the point where I want to evaluate the limit. So I'm going to evaluate the directional limits and see if they exist and if they agree with each other. Okay. So for x greater than 0 and close to 0, x is positive, then h of x is equal to 1. Okay, so h of x is equal to 1, h of 0 is equal to 1, h of x minus h of 0 is equal to 1 minus 1, which is 0. Then the difference quotient is this difference, which is 0, divided by x minus 0, which is 0. So the limit as x goes to 0 from the right of the difference quotient is the limit as x goes to 0 from the right of 0, which is 0. Okay, for x less than 0 and close to 0, x is negative, so h of x is equal to 0. So then h of x is equal to 0, h of 0 is equal to 1 by the definition of the Heaviside function. Then h of x minus h of 0 is 0 minus 1, which is equal to minus 1. Then the difference quotient is minus 1 over x minus 0, which is equal to minus 1 over x. So then the limit as x goes to 0 from the left of the difference quotient is the limit as x goes to 0 from the left of minus 1 over x. We've already discussed 1 over x as x goes to 0. So this does not exist. Okay, so then what do we have? We have that one of the directional limits does not exist, so the regular limit, which is the derivative at 0, does not exist. Okay, what about closest linear approximations? Well, at x naught greater than 0, the graph of the function looks like the graph of L of x is equal to 1. At x naught less than 0, look at the graph of the function. It's locally linear. It looks like the graph of L of x is equal to 0. And at x naught equals 0, we can't really speak of a linear approximation because we cannot speak of a derivative. Okay. Next example, the absolute value function. I'll remind you the absolute value function. If x is greater than or equal to 0, absolute value of x is equal to x. When x is negative, we multiply by minus 1. The absolute value of x equals minus x. You multiply by minus 1 to return a positive number. So for example, f of 3 is the absolute value of 3, which is 3. F of minus 3, absolute value of minus 3. Well, minus 3 is less than 0, so that's minus of minus 3. The double negatives cancel, and you get 3. Okay, so the derivative at 1. F of x equals absolute value of x equals x. F of 1 equals the absolute value of 1, which is 1. Right? We're taking x very close to 1, so that implies that x is positive. Then the difference between those two is f of x minus f of 1 is equal to x minus 1. So then the difference quotient that we need is f of x minus 1, f of x minus f of 1 over x minus 1, which is x minus 1 over x minus 1, which is 1. So then the derivative at 1 is the limit as x goes to 1 of the difference quotient, which is 1. So the limit as x goes to 1 of 1 is 1. Okay. The derivative at minus 1. Okay. If you're taking x very close to minus 1, that means the absolute value of x is equal to minus x. So f of x equals absolute value of x equals minus x. F of minus 1 is absolute value of minus 1, which is 1. Then the difference in the numerator of the difference quotient is f of x minus f of minus 1, which is minus x minus 1. Okay, then f of x, then the difference quotient, f of x minus f of minus 1 over x minus minus 1 is minus x minus 1 over x minus minus 1. That's the negative of x plus 1 divided by x plus 1, and that's equal to minus 1. Then the derivative at 1 is the limit as x goes to, the derivative at minus 1, sorry, is the limit as x goes to minus 1 of the difference quotient, which is minus 1, and then you get minus 1. So the derivative at 1 is 1, the derivative at minus 1 is minus 1, and the derivative at 0, again, we're going to be taking a limit of a function, and that function changes its behavior exactly at the point where we want to talk about the limit. So what we want to do is we want to take directional limits and then check for agreement. So the directional limit from the right, note that if you're going from the right of 0, which means you're taking positive numbers. So x is greater than 0, and implies that absolute value of x equals x. So the limit as x goes to 0 from the right of f of x minus 0 over x minus 0 is the limit as x goes to 0 from the right of x minus 0 over x minus 0. That's equal to the limit as x goes to 0 from the right of 1, and that's equal to 1. Okay. Now, the directional limit from the left, so you're taking numbers, x means numbers left of 0, negative numbers, x is less than 0. That means absolute value of x is equal to minus x. So the limit as x goes to 0 from the left of absolute value of x minus 0 divided by x minus 0 is the limit as x goes to 0 from the left of minus x minus 0 over x minus 0. So drop the zeros, you got minus x over x. So that's the limit as x goes to 0 from the left of minus 1, which is equal to minus 1. Okay, so the directional limits exist, but they don't agree with each other. So the regular limit, which is the derivative, does not exist. So this function has no derivative or no defined derivative. The derivative does not exist of the absolute value function at x is equal to 0. So here's a question. Give me an example of a function f that is continuous everywhere and differentiable everywhere except at x equals 2. So by that I mean it's continuous and it's continuous everywhere, and it's differentiable everywhere except at x is equal to 2. Okay, so such a function would be the absolute value of x minus 2, or the absolute value of x minus 2 plus 7, for example, would have this property. Okay, so now we come to the link or the relationship between continuity and differentiability. If f is differentiable at x naught, then f is continuous at x naught. Equivalently, if f is not continuous at x naught, then f is not differentiable at x naught. However, continuity at a point does not imply differentiability at a point. So the absolute value function is continuous at x is equal to 0, but we saw that it is not differentiable there. If you recall the Heaviside function, It's not continuous at x is equal to 0, and so it will not be differentiable then. Okay, the absolute value function again. The absolute value function is continuous at x is equal to 0. It's continuous everywhere, in fact. But it's not differentiable at x is equal to 0. It's differentiable everywhere else. Okay. So in the next segment, we go on to consider a few examples of using linear approximations.